We've got the Midori team presenting on their security and architecture, and I know this has actually been a topic of interest to this community for quite some time. So Jinsong and I talked about this late last year, and all the planets aligned. So he's going to represent this. Should be very interesting. The next topic we have coming up is Scott Charney's RSA keynote dry run. That'll be on January 29th. And I encourage all of you to attend that. In the past, there's been a lot of great community feedback, which has actually materially changed his keynote. So please do come to that. And then as a reminder, if you attend multiple events, you'll be eligible for the Byte meeting later this year. So on that note, I'll turn it over to Jinsong, and then the surveys will be sent out at the end of the talk. So thanks.
Thank you, Scott. Can everybody hear me? Okay. So today I'll talk about security in Midori. I see there are a few Midori folks here. Pavel is here. Christoph is here. Yao is here. So feel free to interrupt and ask hard questions. They will be the one answering the questions. So security is a pretty big topic. I kind of break it up into multiple areas. We will go through one by one. Again, feel free to interrupt. I don't have enough content to run 90 minutes, so questions are welcome. Before we dive into security, I want to give you a very brief history of the Midori project. Some of you may be familiar with it. Some of you may not be familiar with it. So it is a system incubation project. The idea is if we can throw away all the backward compatibility baggage and start from scratch, what can we do to innovate, to create a new operating system and runtime programming model, application model on top of it, to carry the technology forward for another 20, 30 years. So that's the overall ambition and the dream. The project has been going on for quite a few years. I checked the history. The first sprint dated back 2006. I joined the team in 2007. I think Pavel joined the team shortly after me. Midori does share the same root as Singularity. So Singularity is a research operating system created by MSR, Galen Hunt, Jim Laris, those guys. So when Midori started, we look at Singularity. We say, this is pretty cool. There's a lot of principles that we want to follow. They already did it. So we started from Singularity code base. Since then, we have kept a lot of the principles from Singularity days. Most of the code is already rewritten. We did add a lot more stuff and change a lot of stuff. But a lot of the principles are still same from the Singularity root. Late last year, a couple months ago, we joined operating system group. So we're now part of the operating system group. Actually, part of Midori just moved to building 10. We're sitting together with Windows kernel and the hypervisor guys together. Happy family. So that's where we are today. In the next few months, we will figure out where Midori is going, right? Does it make sense to kind of combine the good side of Midori into Windows, make Windows better? Does it make sense to continue on the independent Midori path, shape Midori in some way? There's a lot of open questions from the reorg. We don't know all the answer. We're working hard to figure it out. So when the project started, there were a number of goals we want to achieve. The number one goal is security and reliability. And Chris Broom summarized that in a sentence called correct by construction. What does that mean? It means I don't want to get the quality by doing tons of stress testing and ship to user complaint, all the stuff. I want to get the quality by writing the code, the compiler compiles the code, there are a bunch of static tools to analyze the code, and the compiler is happy, the tools are happy. I know there's some correctness guarantees in there. We want to present developer a platform where there's a bit of success, where they naturally just go towards the good quality code and step away from the bad quality code. That's the number one goal for the project. And of course, you can build the most secure system. If it doesn't perform, nobody will use it. So the secondary goal, we need good performance, good scalability, and small system footprint. And also, we want to have good developer productivity, right? You don't want developers to spend tons of time on the ceremonies. You want them to worry about their business logic. So this is the basis of the entire presentation. This is the system overview of a Midori system. Down here in supervisor mode, run 0, we have the microkernel. And up there, we have one or multiple domains. So what is a domain? In Windows, you will think of this as a process or a user mode address space. In Midori, we don't call it a process. You notice we have process up there. The reason is in the same address space, we actually co-host multiple processes, multiple user mode processes up there. So microkernel manage virtual logical processor, scheduling, it manage interrupt dispatching, manage physical memory, it manage lifetime of the domains. Up there, there's a domain kernel. The domain kernel manage everything happens in this domain or in this address space, right? So it manages the virtual processor scheduling. It manages the virtual memory in the address space. It manages the virtual interrupt dispatching. It manages the lifetime of the small processes. We will talk about this in later slides as well. So each process up here has its own runtime. It has its own garbage collected heap, right? So they don't share the same GC heap. If you have an object on the GC heap, it's limited to that process. You can't make that object visible to another process, even though it's in the same address space. So how come we can make multiple processes running in the same address space? What kind of isolation is in there? The trick there is, this is what we inherit from Singularity, what we call software isolated processes, right? So in the processes up there, third-party code, you are not allowed to write either unmanaged code or unsafe code. It has to be verifiably safe. Otherwise, the compiler will not compile, the loader will not load. Because the code is verifiably safe, even though you have multiple processes running in the same address space, nobody can touch each other's state, right? So the isolation is achieved that way. So the isolation boundary there between processes is actually fairly strong. You can think of that as if the code is running inside the process at arbitrary instruction boundary, we can rudely kill a process with no coordination at all. Kill that process disappears. No other processes in the same address space will be affected by the death of that process. That's the strength of the isolation. So isolation boundary is actually fairly strong. The runtime here includes the GC, include inter-process communication, include a bunch of stuff. The key here is the software isolated processes and multiple domains. So there is hardware isolation between different domains. It's a traditional address space isolation. So starting from this slide, I will talk about from different angle, I will talk about the security aspect of the system, and I'll keep referring back to the previous slide, and we will drill down to details. So number one is we use managed code, safe managed code, wherever we can, all right? The vast majority of the system is written in managed code. Network card driver, disk driver, TCP/IP, web server, web app framework, file system, storage, everything is written pure, safe, managed code. All right? So what is in either unmanaged code or unsafe code? There are some. There are the microkernel down there running in supervisor mode that is entirely written in C, C++, and assembler code. Right? We didn't try to put managed code down there. The domain kernel is partly written in assembler code, like context switch. We do have user mode scheduling in domain kernel. We do have to do context switch, and it's impossible to do without using assembler code. They're also part of the domain kernel written in C#, but it's using unsafe C#. One example is the memory manager. The domain kernel has a memory manager manage the virtual memory, the virtual address space, right? That include memory allocation, memory free, all the stuff. So that has no dependency on the garbage collector at all because of the layering concern. GC is sitting strictly on top of the memory manager, and the memory manager is written in C#, but it's unsafe C#. We do use pointer operations in the memory manager. There's no way around. The garbage collector itself is written in C++. That we didn't write it. We inherited from CLR and Red Hawk. It's already there. It makes sense. We just took it. So for those, we have no plan to rewrite them in managed code later. They are considered the lowest level of the system. They will remain unmanaged or unsafe. There are also some unmanaged code we just pick up around the company for different reasons. One example is Enigma. If you're familiar with that, that's the all cryptographic library, all cryptographic functionality are implemented in Enigma. There's a company policy say, you shall not implement your own crypto primitives because you will get it wrong. So we said, okay, we'll follow that. We'll just take Enigma code, binary drop. We will not try to innovate there. That's not our strength. So even though I'm giving a security talk, we are not innovating on cryptographic stuff. It's just Enigma code. We take it over as is. We take the binary drop. ACPI, we didn't re-implement it. We could, but we just decided not to because guess what? The different hardware over the years, they have hardware bugs. There's so many errata we have to worry about. It just makes sense to pick up a solid ACPI implementation that handle the existing hardware, know where the bugs are, their workarounds, just use it, right? They are also considered the lowest part of the system. There are also some unmanaged code we picked up for scaffolding purpose. It's not like we want them in the system for the long term. It's for the expediency of the progress. We just take them in. When we really need to, we can rewrite them back in safe managed code. Example, there's some multimedia component like echo cancellation, H264 decoder, those stuff. We just say, there's large chunk of code. We can re-implement it, we can port it, but we just decided not to in name of faster progress. So we took them. Whenever we want to, we can rewrite them in safe managed code. We know how to do them, right? But the rest of the system are all safe I'm# code. So I didn't say what I'm# is. You think I'm# just basically is a C#. It's C# with a few more keywords. Those keywords give you immutability guarantees and give you concurrency safety guarantees. We'll go through that later. So it is basically C# with some more keywords, and it's actually 100% compatible at MSIL level. We didn't touch the MSIL specification at all. All the keywords translate into attributes for the backend compiler. So the implications of using managed code in vast majority area of the system is there's memory safety and type safety that you can rely on. Like the software isolated processes concept will not work if part of the user application is written in unmanaged code or unsafe code. It just doesn't work. It falls apart. large category of traditional security problems simply don't exist. Buffer overrun, it just can't have that unless you have a bug in your compiler or in your runtime, right? Otherwise, you just cannot write a piece of code that say, I can buffer overrun this in safe managed code. You just can't do it. Heap corruption and stack corruption, again, unless you have a bug in the runtime or in the kernel or in the compiler, it just simply can't happen. No double free. You can't use after free. So that's a large category of security issues. They just disappear automatically. You just don't have to worry about them. In Midori, we have the concept called closed processes. What does that mean? It means at compile time, you already know all the code you will run in that process. When you start that process, before that a single instruction in the process is run, you already load all the code. There's no dynamic code loading, no load by library, right? The implication of that is it allows comprehensive compile time static analysis. With load library, because at compile time you don't know all the code is running in the process, it's kind of hard to do static analysis and figure out what the process will do. With closed process, you have all the information you need. Now it's just pure computing and science to figure out with all the information what I can derive out of it and what I can do analysis and verification. Yes? Right. The question is, what about dynamic language like JavaScript? So we do have JavaScript implementation. JavaScript does use its jitter to jet code and run the code. So dynamic language like JavaScript doesn't live in the closed process model. All right. So remember, we have multiple domain concept. If you feel like, I'm going to run a piece of JavaScript, I don't feel comfortable with the origin of the JavaScript, or I don't feel comfortable with what security implication I have running that. You could decide to run that in a separate domain or in a separate address space, and you rely on hardware isolation to protect yourself, right? But again, the fact that the process will use JavaScript runtime is known at compile time and load time. So you can make the policy decision upfront, how much you trust the process. Yes?
In the slide where are the
Device drivers. I will talk about later in this slide. I have a slide for that. Yes?
So if I were to write a vicious studio, new vicious studio from Midori, I could
So the question is, if I write a Visual Studio on Midori, I can't because I can't do add-ins. The answer is yes, you can. You will be able to do add-ins, but the add-ins will not work in the form of load library. The add-ins will work in the form of create process. Right? You run add-in in a separate process. You use inter-process communication between the host and the add-in. You can terminate the add-in at will. It's actually a solid story there. And because everything is a process, the inter-process communication is extremely critical for performance. We optimize IPC quite a bit, so performance is good.
right. So let's say I have a complex syntax tree and some model. How do I share that across
Right.
big data?
So the question is, how do you share big data structure across processes? Let me answer that later on, because later on I'll talk about microkernel architecture in some of the slides. When I go to that slide, I will answer this question. Okay. Closed processes also enable us to do capability-based security model, which I will talk about later in the slides. It also removes some runtime failures. If you're familiar with .NET, when you make a call, and that call is in a different assembly, and the runtime have to load that assembly at runtime, you may get a file not found exception, or assembly load failed exception. Sometimes it's weird. It's like, I'm not even accessing a file. What do you mean file not found exception? It's trying to load the DLL, and that load failed. So by using closed processes, you don't have that runtime mode failure, which impact the error model, which I'm talking about next. So in Midori, we have a very, very strict error model. The preference here is I prefer immediate and deterministic process termination over my state might be inconsistent, might be consistent. I kind of don't know, but let's continue running and see what happens. Right? So I have a few slides covering the error model. You will see it is very strict. So we start with arithmetic. All arithmetic, addition, subtraction, multiplication, they're all checked. By default, if arithmetic overflows, your process terminates. You cannot handle that error. You're not allowed to handle that error. There's no way for you to handle that error. The process terminates right there. So in this example, right? Let's say you, you have a function, say, is the range valid? I have a starting point. We have a number of elements, and I have an upper bound, right? And I will use this function to make a security determination to whether to give user access. And if you write this in C or even C#, if start plus count overflows, well, it just silently overflows. And you will make the wrong decision. There are security vulnerabilities because of this. In Midori, if start plus count overflows uint.max, boom, process terminate right here. There's no way to handle it. So you say, okay, that's tough. How do I write this correctly? Well, there is a way to write it correctly. You can use unchecked keyword. It is explicit. You have to write this down. So you say, I want to handle error overflow. I will just treat overflow as returning false. That's fine. You use unchecked keyword says, I'm handling overflow myself. Don't kill me. Then if overflow happens, this will be false, and you return false. Right? The same applies to number conversion. If you have an integer, you make a cast down to byte or a 16-bit integer, and it overflows, boom, you die. If you divide by 0, you die. If you try the smallest negative number into that mean value, and you do absolute value on it in C#, what do you get? You don't get in that max value. You get in that mean value, right? Even though you did absolute value on it, it's still a negative number. Well, in Midori, you die. So it's just pretty tough, right? It is hard to live in. So we say, okay, we will give you some relief. We give you some helper functions where you say, I really don't know before I call this function whether overflow will happen or divide by 0 will happen. So there's a bunch of helper functions to do try get absolute value, try divide kind of thing. But the key here is extremely explicit, right? If you write code in the straightforward fashion, you get the safety guarantee, although you might die. If you know, I don't want to die, I want my code to continue running, you can use these helper functions or you can use unchecked keyword, but it is very explicit in the code. In code review, it's very easy to detect. You can use editors, IDEs to search. It's explicit. Yes?
How often did you have to use these try variants yourself?
The question is, how often do we have to use the try variance or unchecked keyword? Not too often. We use this almost exclusively in parser and decoder, where we have incoming data from untrusted source. We're parsing it or decoding it. We might get into divided by 0. We don't know, but we want to handle it, right? In that case, we certainly don't want to crash if the incoming data is bad. So decoder and parser, there's certain usage of this. For unchecked, it's also decoder and parser, and also in very, very limited few cases in the system where we say the performance is so critical, we cannot tolerate that one conditional branch. We use unchecked. But again, you can search the code and figure out. Oh yeah. Generating unique ID or perf counter update, the stuff that you kind of know it will overflow, or rim buffer index that you know will overflow, you use it. Or it's performance critical, you use it, or decoder and parser. Another aspect of strict error model, preconditions. So if you're familiar with CLR and .NET framework, everything is modeled as exceptions. If you have an array with 5 elements and you index into it and say A bracket 10, what do you get? You get index out-of-bound exception, right? In reality, it really is a bug. If you have an array of 5 elements and you try to access the 10th element, it is a bug. You shouldn't do it. So in Midori, that is immediate process termination. There's no way you can handle that error. You fix your bug. All the APIs carry precondition, requires something. That's the syntax of the precondition. If the precondition check fails, it's immediate process termination. You cannot handle that error. So that makes it hard to program the system, right? But the nice part is the precondition is part of the API signature, right? So it's part of the versioning story. So when you write code targeting some API, you actually know what that API is expecting. It's actually better than, here's my implementation, here's the entry point. I say, if something throws this exception, if something throws that exception, that's not part of the signature. The best you can do is you document in MSDN, right? Here, the tool will generate the document for you, and the compiler can actually check some of the preconditions for you. It's part of the signature, it's part of the versioning story. The caller is responsible to synthesize the parameter values before passing in. If the caller failed the precondition, it's considered a bug in the caller you have to fix. So again, in parser and decoder, where you have unknown data, what do? So there are part of the platform where we, again, enable this try pattern. For example, if you have a dictionary, you can do try lookup. I don't know if the key exists in there or not. I do a try lookup, I'm in good shape. But if you say, I'm going to use the indexer, here's the dictionary, I use the bracket syntax to do the indexer, then you better know the key exists before you do that. Another aspect of the strict error model, there is no out-of-band exception. What do I mean by out-of-band exception? They are the exceptions you don't throw yourself. There's no throw keyword in the code. The system kind of throw them for you, right? For example, in .NET, if you need to dynamically load the DLL and the DLL cannot load, you will get exception. If someone calls thread abort on you and you're running, you get thread abort exception. If you're running and you allocate something and the system ran out of memory, it cannot allocate for you, you get out of memory exception. In Midori, all these are immediate process termination. You cannot handle it. So out of memory is an interesting case. How can I write a reliable system if I cannot handle out of memory exception? Right? The way we do it is we do hardening from outside instead of hardening by handling out-of-memory condition internally in the code. So here's how you think about it. In the traditional model, It's kind of first come, first serve, right? I'm a fat process. I live on a 2 gig machine. I allocate 2 gig memory. Well, the system will just give me everything. Another one come in, and he said, I need a 64K memory, please. No, you can't, because 2 gig is already gone. First come, first serve, regardless who is more important. It's kind of suck. So in Midori here, what we decided, we say, we will have, by doing installation and administrative policies, we will know which process is more important and which process is less important. If the system runs out of memory, then we have to kill something. We don't kill the allocator, right? So the one who requests the memory. We kill the one who is less important. In this world, even if you're not allocating, you can still be a victim of auto memory. You can still be killed because you're not important, right? And this, I think, in general, it gave us a better system, overall better system behavior. And also, from experience, we know handling auto memory from within the process by looking at the errors and doing backout is extremely hard. You just can't get it right on any scale. For small amount of code, yes. For large amount of code, it's impossible to get it right. So we actually like this model. What about Stack Overflow? Well, in Midori, it's not a contiguous stack. It's actually stacklets. It's stack segments. It's discontiguous stack segments. So stack allocation is actually just memory allocation. So Stack Overflow is equivalent to auto memory exception. So in Midori, there's no auto memory exception. If you Stack Overflow, you get terminated right away. I already covered a rebound check. If you go out of bound with reindexing, right away process termination. If you dereference a null, you get terminated. And if there's access violation which is not dereferencing null, we actually terminate the entire domain, the entire address space. The reason is no safe code is supposed to be able to cause non-null access violation. If we see that, it's an indication of a bug in the runtime. It means the runtime, the trusted runtime, already have some corrupted state. We cannot trust anything running in that address space. So we actually kill the entire domain. After you go through this list, yes? So the question is, what about in the browser? I have different tabs, right? And if I kill, all tabs are gone. The answer is you use one process per tab, per site. Yeah, Pi will correct me. It's even stronger than that. Yeah, so I'll cover some more related material later, but in Midori, the story really is you want to get the process scope smaller, right? Traditionally, like SQL Server, it may be one monolithic big process. In Midori, you don't want to write your code that way. You want to break it up into multiple processes by both decomposing vertically and scale out horizontally. I'll touch some of that later on. Other questions? All right. So after all this list, now you know there's no autoband exception. The system doesn't throw exception on your behalf. All exceptions are thrown by the throw keyword in the code. So that's why we can have the declared exception model. Oops, sorry about that. When you have a method that might throw something, you declare throws keyword on that method. This is part of the signature. This is part of the versioning story. When you call that method, here's an example, right? You say bar calls full. Oh, compile error. Why? Because full throws the exception and you are not handling it. It doesn't compile. You can say, okay, how about I just propagate the exception up? I don't want to handle it. I want my caller to handle it. You can't. It's compile error. Why? Because bar is not declared as throws, which means bar cannot throw exception, which means you cannot propagate exception out. So it's a compile error. You can't compile it. What about this? This compiles just fine because you're calling full in a try block. So you're catching the error. This is fine. Or you can say try catch. This is a new keyword in M#. You can say try catch, calling it, and you get a result of int instead of int. And now the result of int, you have to say, is this successful or not successful? You have to do that check. Here's another example where bar is declared, say, I might throw exception. In this case, you are allowed to say try full. If full throws, it simply propagate, right? So the point of this language features really is I will make error handling explicit. I will make error handling part of the versioning story. If your V1 API didn't throw exception, your V2 API throws exception in the traditional platform, it's not versioning breaking change. You're allowed to do it, and the poor caller just doesn't know, right? Poor caller says, I'm targeting your V1 library. You don't throw exception. I don't need to handle anything. I don't need to worry about the consistency of myself. Well, in V2, you throws, the assumption is false, and you kind of get into state inconsistency problem. In this world, if you change full from not throw to throws, well, it's a versioning breaking change. All the code calling it will not compile, right? You force the developer to have to go through the code to re-examine the assumptions and put in the right thing. Yes, question? In this world, can you not discriminate between exception types? We do have optional typed exception. So it's kind of like Java. Not only you say throws in full, but also here, you can say only throws file not found exception kind of thing. If you do specify it, the runtime does help checking just like Java. It is optional because we do worry about versioning story. Christoph can give you more background there on how we make the decision and the guideline. Yes. The question is, in the code, can you catch specific type of exception? Absolutely. Just like C#, you can. And can the code know he handled all the exceptions? That is required. If you don't handle all the exceptions, you will not compile. So, for example, if full declares, I only throw file not found exception, then here you can say catch, you can say catch exception, or you can say catch file not found exception. It all compiles. All right? In this case, full didn't say only throw, which means it can throw the base exception type. If you only say here, catch file not found exception, but there's no catch exception, the code will not compile. You have to catch everything or propagate everything. One way or another, you have to do it.
Can you use this try function syntax with a function that doesn't throw? So if true wasn't declared to throw?
Nope, you cannot. So the question is, if full is not declared as a throws function, can I still say try full? Nope, it will break. It will not compile.
What about the old syntax of try bracket?
That is fine. You can have try bracket. Nope. Okay, I will correct me again. So something in there have to throw, otherwise it's a compile error. John. Yeah, it's not the exception. It's immediate process termination. You cannot catch it. Yes. Yes. So the question is, if some function used to throw and in V2 it doesn't throw anymore, it's a versioning breaking change, absolutely. Yeah, so Christoph mentioned something, which is that the implementation of the function can choose not to throw exception, but you can keep the throws annotation up there. That's not a versioning breaking change. Right? Yes, throws and preconditions are both part of the signature. They're both part of the versioning story. Do we have a debugger for this thing? If so, is it type safe? Yes, we do have a debugger for this thing. It is written in M#, it's self-hosted. The debugger runs on Windows, not on Midori. So is the debugger type safe? The debugger is written in safe M# code running on Windows. But obviously, the debugger can break type safety of the debuggee because there are commands in the debugger say, write memory. So we talk about the strict error model, right? They are very, very strict. What are the implications of the strict error model? So, so far you get the sense. By default, the system follows a very strict order. You leave within your boundary, you step out, we terminate the process right away, deterministic and immediate. We prefer process termination over continue running without knowing for sure the state is consistent. So that makes the system easier to crash, easier to be denial of service, right? But it is harder to go a step beyond the denial of service, privilege elevation, remote execution. They are much harder, right? So definitely there's a balance, right? Easy to get denial of service, but it's also easy to diagnose. When the process terminates, you get a dump, you know exactly what happened, you find the bug, you fix your bug. So it's a good decision or bad decision. It's in certain cases, if you just measure the reliability of the system or the service, I would say it's a balance. Overall, in the long term, I'm a strong believer this is the right decision. When you first develop, you may see more crashes than you used to, but it's a good thing. All exceptions are explicitly declared and thrown. Caller of throws must explicit handle. So everything is explicit. All right, next point. There is no shared mutable memory cross process boundary. Regardless, they run in the same address space or in different address spaces. So memory can be shared. In the I/O stack and data stack, we actually do zero copy I/O fairly efficiently. Memory can be shared. But before you can share a piece of memory, you have to make the piece of memory immutable. And the language, the compiler, the verifier, they all work together to help you to check it. If you just can't share a mutable memory. The API simply doesn't exist. So if you have a piece of memory that is mutable, it is exclusively owned by a single process. There's no way around that. The implication of that decision really is there's no time of check, time of use issue across process boundary, which is a fairly large category of security vulnerabilities where they come from. It also makes it harder for a process to exploit bugs in other processes by, hey, I give you some garbage data, and by the way, I'm tweaking it while you're accessing it. It is hard to achieve that.
So in all of the conversations here, you haven't started talking about some of the bugs that show up once you move to an all-managed programming language like C#. In there, at the end of .NET 1.1, we found a whole class of problems around resurrection and handle recycling. I suspect that you guys may also have handle recycling issues if you allow handles to work at the domain level. Have you guys thought about this?
So question is, what about resurrection? What about handle recycling? So First, let's talk about handles. There is no handle recycling. I actually will go through that slide, but I will talk about it now. There is no domain level handle, period. That is visible to processes. There are domain level handle visible to domain kernel, that's for sure. But if the domain kernel need to kind of make some domain-wide handle visible to a process, it will wrap it in a process handle. It will not expose the domain-wide handle to the process code. And not only that, we also want full length to make sure there are no thread interleaving in the process. I do have slides for that. We'll talk about that. Actually, that's the slide. Yes?
I have a question regarding time of check.
Yes.
What about this issue with process?
In the same process, multiple threads, we're going there. There are no threads. Of course, there are threads in kernel and in process runtime. Yes, there's a question. So the question is, I need to understand the question. The question is, if you have a parser that's untrusted code, no? Okay. Right. Right. So the question is, if we put a parser in a separate process because it's processing untrusted data, and somehow we manage to compromise that parser process, then untrusted data will come back to the originator. Absolutely. If you can compromise a process in the system, then you can use that process as a beachhead, right? And depends on the level of penetration and compromise, you may be able to do different level of bad things. For example, if you can compromise memory safety or type safety of a process, then because the software isolated processes entirely depends on memory safety and type safety to isolate between the processes, that means you actually compromise the entire domain, the entire address space. Right? If you didn't manage to compromise memory safety and type safety, but you compromise some business logic, then you could get some garbage data back. But in that case, still, there's no time of check, time of use issue because you get garbage data, but the garbage data is immutable. You get immutable garbage. All right, so threading. Public API, third-party code. There are no API to create thread. There are no API for you to do log, semaphore, event, monitor. No such API. There's also no log-free inter-complex change. Nothing, absolutely nothing. In the kernel and in the lowest level of runtime, we do have this subset of this. We do use them, but they're never exposed to third-party apps. No, we don't have a finalizer thread.
And we don't have resurrection.
So the finalization story in Midori is interesting. Personally, I actually don't like where we are in finalization, but I'll describe it anyway. So Midori uses post-mortem finalization, where you have object pair. One object is the pre-mortem state, another object is a post-mortem state. The post-mortem state object contains the resource, the real handle. And the pre-mortem state is the sentinel. So in the garbage collected world, once the pre-mortem state become unreachable, there's a weak pointer from the post-mortem object pointing to the pre-mortem, and the weak pointer says, aha, the pre-mortem become unreachable, that link of the weak pointer become invalid. That's when garbage collector knows, okay, now I can run finalization on the post-mortem object, all right? And then what happens is Midori execution model is, you can think of that as a big Windows message loop. It's a single-threaded big loop, right? The unit of work, we call it to-do. So the message loop is processing many, many different to-dos. One of the to-dos is a finalization to-do, which means it will just queue all the post-mortem object on a queue until the single-threaded scheduler says, I'm ready to process finalization stuff. Then it will just go through the queue and call the finalizer one by one. It's on the same thread, not on a different thread, because there's no thread. So by default, processes in Midori are single-threaded. You break into debugger, you look at how many threads are in there, exactly one. There are data parallelism and task parallelism APIs. There are safe APIs, but by default, if you don't use either data parallelism or task parallelism APIs, you get exactly one thread in each process. Yes, question?
So it sounds similar to an NYM task scheduling. And other people have tried NYM task scheduling. They run into problems. You mentioned earlier that you have a task segment you're allocated. Other people with task segmentation, they run into problems with certain applications having memory. Like on recursive algorithms, we get a lot of recursive data that allocate a lot of task segments to the recursion, then it goes away, they have the garbage segments that they clean, and then it all happens over and over again, and the garbage collector just wants to be able to handle the
Right. So the question is, sounds like N by M scheduling, and what about deep recursive algorithms where it use a lot of stack segments and make garbage collector crazy? So first of all, personally, I don't think this as N by M scheduling. I think this as the N-to-1 scheduling, because remember, each process is single-threaded. All the to-dos scheduled in there is on a logical thread, not on M logical threads. It's on one logical thread. Another one is even though we use stack segments, the stack segments are deterministically cleaned up. They're not garbage collected. So before the function call, we look at the stack size requirement of that function frame when we decide whether we need to link another stack frame for the execution or not. And if we do need to, and after the function returns, on the return arc, we actually return that stack segment back to the look-set list right away. We don't wait for garbage collection. If we do wait for garbage collection to clean up the stack segment, we're going to have a big fat problem. There's no question about that. OK. So continue on the slide. If there are no thread, how do you achieve concurrency and scalability? Right. So first of all, one observation is in traditional system like Windows and Linux, sometimes you use threads, not because you need to use multiple processors. It's because you are calling blocking APIs, right? There's a thread driving the UI update. I need to call some API. It might block for a second. I want my UI to remain responsive while I do it. I don't really need the two processors to run them at the same time, but I just need to make sure my UI is responsive. So because of blocking, you create a worker thread, call that, do the rendezvous and everything. In Midori, there is no blocking call. All I/O are going through IPC, and all IPC are asynchronous. There's simply no blocking APIs. So the need to create thread to satisfy blocking call and responsiveness together is not there at all. So you need concurrency and you need parallel execution only if you truly want to use multiple processors. That's it. So how do you use multiple processors? First of all, you either decompose or scale out to multiple processes. I use different words, decompose or scale out. What do they mean? Decompose means, let's say I have a multimedia stack, right? There are different parts of that. One thing is doing audio decoding, another thing is doing decompression, another thing is doing the sync between audio and video. Do they need to be in the same process? Sometimes yes, sometimes no. If you architect correctly, sometimes you can actually break them into different processes. So a couple years ago, we built a Midori video chat system where there's a multimedia pipeline. We actually have more than 10 processes in the pipeline. The data actually travels through more than 10 processes. They're separate vertically. Each process do different work. And it's actually very responsive. And the performance impact of the cross-process communication, it just doesn't show. So that's one way to use multiple processors, you kind of pipeline. Another one is scale out. It means I have multiple instances of the same code running. A typical example is a web server, right? If I have a web server, a single web server is single-threaded, means I only use one processor. But if I use 16 processes, they're all the same code. They're just running in parallel. Then I can use 16 cores. So decompose and scale out, they're both very commonly used in Midori to break one large piece of functionality into smaller processes. And by definition, you get parallel them that way. Also, inside the process, you do get data parallelism APIs and task parallelism APIs. They are structured. They are safe. You cannot break concurrency safety using the APIs. Because of all this, there's no instruction-level thread interleaving concerns. Right? In the traditional threading world, each instruction might interleave something. When I run this instruction and I run the next instruction, the world might have already changed on me. It's very hard to reason for humans. In Midori, that simply doesn't exist. The interleaving, the state change can happen. It can only happen at the turn boundary. The turn is what I mentioned, the to-do, the work unit. And it is clearly visible in the code. Here's an example. Await is a keyword that denotes a possible turn boundary. So the implementation of this basically says there might be a turn boundary in this function. And you just read the code and you just search for await keyword. And you say, aha, from here to here to here, there is no turn boundary. The state will not change. But here might be a turn boundary, which means the execution might be parked here. The big message loop might be running something else. And 1 minute later, it may come back and continue running this piece of code because this is doing I/O. Right? So the turn boundary is here. So whenever you see await, that's a possible turn boundary. If you don't see await, there's no state interleaving. The state before you come into the block will be the same state as you exit the block. So again, it's not we eliminated everything. It's just we make it much easier to reason about. Right? It's explicit. It at very coarse granularity.
On this, it sounds like you've done a lot of things to remove the ability to run multiple threads at the same time. And yet, if you were running, say, a web server, you're going to have to deal with the possibility of denial of service attacks. How can you run something else to essentially be a watchdog to kill parent if you have this turn model that's very...
Right. So the question is, how can you create a watchdog to watch denial of service and kill threads? The answer is you don't kill thread, you kill processes. The watchdog is a process. It monitors the health of other processes, and you can safely kill process. So there's a theme, right? when you think about thread, sometimes you just escalate up into process level. That's the way you do it. We also have some, oops, sorry about that. We also have some language and compiler feature to help you further reasoning about concurrency safety. We call TSE, taming side effect. So the language features basically allow you to reason about immutability. In C#, there's a read-only keyword. Read-only keyword doesn't help that much because it's shallow, right? In Midori, there's annotations that are deep. For example, if you say immutable full, that means the entire object graph, starting with the variable you're referring to, the whole thing is immutable. It is frozen, it cannot change, period. Or you can say it's readable. Readable is much weaker than immutable. It just says, I give you this object graph. You cannot modify the state. Somebody else might be able to modify the state, and you have to expect the state change. But you only expect the state change at the term boundary, not at instruction boundary, right? Writable is the C# default, which basically says, here's the object graph, do whatever you like about it, you can do whatever you like, right? Isolated says you're the single owner of the object graph, and you can do whatever to it, and at the end, you can freeze it into immutable, right? Only isolated can be frozen into immutable, readable and writable cannot. So their language features, of course, the compiler guarantees when you have this annotation, it is checked and checked at compile time, not runtime. So remember I mentioned the data parallelism and task parallelism APIs. The rule is only immutable object graph can be shared across the data parallelism and task parallelism boundary. And as a corollary, all static fields are immutable. You are not allowed to have mutable statics. It will not compile. So all this just help you to do the reasoning of invariance and state change, where they are, where it's impossible. The implications of the concurrent safety is actually I already went through quite a bit this. No instruction level interleaving, time of check, time of use, and resist cross data parallelism, task parallelism is impossible. Inside the same big message loop, state interleaving only happen at term boundary, and there at term boundary, you do need to worry about time of check, time of use. Inside the term boundary, you don't have to worry about it. All right, so so far I've been focusing on the language runtime stuff. This is getting more and more interesting. It's capability-based system. So traditionally, we use access control list, right? Capability and access control list, what is the difference? I have a, oops, sorry about that. Two pieces of code to illustrate the difference. The top part is access control. It says, hey, I have a static method called file.open. Let me try to open that file. It may succeed, it may fail. It may fail because access denied. In the capability model, I just pass in the file as a capability. You do whatever you like with it. Really? There's no difference? The difference here is kind of subtle. Is whether you have a static method to open or access a resource. Whether you have a static method. In the capability model, there is no such thing. Everything is based on the instance. If you have the instance, you can call the method on the instance. There will be no access denied exception. If you have f, you can do f.open, f.read, f.write, whatever you like. If you don't have f, you can't do anything about it. Yes? In that case, you use type system to do it. So you can say, I have a read-only file. and I have a generic read-write file. So you give full a read-only file, it can only read from it. You give it a generic read-write file, it can read and write to it. You use a type system to enforce the capability.
What about since files will be shared, when they are being triggered and actually change
Yeah. So the question is, what about accessing file from a share where an admin can change it on the remote system? So there's a big question about how does the capability-based system interop with the rest of the world, which is access control list based, right? Both worlds are self-consistent, right? The question you ask is exactly cutting through the boundary. I live in a capability-based system where, if pretend there's no remote file system, it's entirely inside Midori, then I can say what you can read and write on the file system is entirely tree-based. If you can write something, you can write everything below it. Then capability-based system just works. But what if I need to interop with file share, with SMB share? So one answer is you can do the interop. You can use runtime dynamic failure to do the interop. Another answer is you pound the question by saying, I only live in certain environments where the access control list conform with the capability model. The true answer is the interop is hard. Yes?
So I'm confused by this example. In the actual example, you're specifying a file to open, but how are you specifying the file that you want in the utility model, right? Like you have a function that takes a file. In the first example,
So actually, let me answer that question after 2 slides. Okay? So in the capability-based system, what don't require capability? We said consuming CPU cycles don't require capability, and allocating memory resource and using memory resource don't require capability. We basically just decided if we put capability on this, it's going to be a nightmare for developers to write their code. So CPU and memory don't require capability, which means if you have a manage object, you can call new. You don't need capability to do it, kind of thing. All other resource consumption require capability. For example, if you need to open a file, if you need to get current time, if you need to get access to a process handle, all of them require capability. Some of them is by nature, because like all the I/O are done through other processes, so you have to go IPC, and the only way to get IPC is you get some capability to talk to the other process, right? Some of them is self-imposed limitation. For example, getting the current system time. We just say we want the capability in place, even though we could go the other way. We want the capability in place. That way, we can reason about what code is deterministic and what code is non-deterministic. The capability provisioning, which is kind of what you were asking. Okay, now all the code require capability. They're all object instances. Who provisioned the capability for me, right? The capability provisioning rolls all the way up to the process entry point. And in Midori, we distinguish between a program and a process. A program is managed by the system. Like browser, you can think of that as a program. I just start the browser. A process, a sub-process in a program, is managed by the parent process. So for program, the capabilities are supplied by the operating system, and they're controlled at installation time. And for child processes, the capabilities are exclusively provisioned and supplied by the parent process. And we don't mix them together. There's no such thing as a subset of my capability is provisioned by my parents. Part of that is provisioned by the system. There's no such thing. It's one way or another. Here's an example. This is a program. It's a real code, copy-pasted from our source code. It's a utility to read perf counters. And this is the signature of the entry point of the program. It's say basically the remotable is a signature. It says, in this program, I'm going to need a bunch of things. Like, for example, I need to get time. Therefore, there's a clock capability. Without this, I can't get time. I have this so that I can create asynchronous activities in this process. And I have this so that I can know myself what is my process ID, what is my process name kind of thing. I can read my own perf counter. I can read the perf counter value from the kernel and the rest of the system. And I get a directory of the other processes, so I can write the perf counters from other processes. By looking at this, you know a few things. You know, okay, first of all, this program requires perf counter capabilities, so it's probably reading perf counters. You also know it didn't request networking capability. Therefore, this program will not talk to the network. You know that when you look at the code. You know it will not interact with the disk because there's no file system capability. You know it will not do any graphics UI stuff because there's no drawing capability, right? So by looking at the program entry point, you already know what the program can do, what it cannot do. This is a capability. So basically, you think of it as the leaf node need object instances to do stuff. They all roll up. Somebody need to provision it. And at the very top is the entry point of the program doing the provisioning. Yes, question? Right. So the question is that in the capability model, how do you control the communication between processes, right? The different processes access each other and they talk to each other. How do you control that? So in Midori, two processes can establish communication in one way, which is one process publish its endpoint and say, I'm a service. I provide certain type of service. I publish myself. Another process somewhere else says, I need a certain type of process. Something to provide it. I need that. That's the only way for two processes to talk to each other. There's no other way, right? Two programs to talk to each other. So by registering yourself and say, I want to provide this, and then the system need to have the knowledge of this guy want to publish a capability to the rest of the system, and what is the mechanism to control this? That is application model. So I'm not talking about application model today. That is actually a very big topic. I'll talk to Soner and see if he want to give a talk, or you can talk to him privately about this. It is a big topic, and it is non-trivial complexity. Right. So the publisher doesn't make this decision. The system makes the decision. There's a strong separation between this, right? The publisher says, I provide this functionality. That's it. The system, the application model, makes the decision who I want to make this functionality available to. So, so in fact, Midori didn't invent this capability model, right? It's actually a fairly common today in the modern app model. Like if you have a mobile device, maybe it will ask you, the weather app want to access your location information. Do you want to say yes or no, right? So in that sense, it is a capability model, right? There's a provider of the location service. The weather app want to use the location service, and you as the administrator of the machine decide whether you want to give the capability to the weather app or not.
So is there no, so if I want to change that, does that mean I have to install the program? Or they configure it?
Right. The key there is it's not a process runtime decision. It is installation and process launch time decision. Either check all capabilities are referenced. No, there's no such check.
So the standard programmer creates one of these things, puts it in a file,
Well, then you run into problem in the installation. The installer will ask admin, hey, this program want to, yeah.
I might need all of this stuff.
Sure, and by the way, it is a versioning concern as well. If you require more capability, it is a versioning breaking change. So the question is, will this give us information we really want? Because developer will just use a standard model to request all capabilities. I think there's some economy at work here, because the more capability you request, the harder for your app to get adopted. I think it is true. If you don't need networking, if you don't need the app to format my hard drive, you shouldn't request it. So I'll stop the argument. This is out of control. So sorry. Yeah. So let me answer the question in this way. In a way, this is not a technical problem. It's not a technical problem. It's a higher level problem, right? There are certain ways we can expose this. For example, you can have a meaningful dialogue with the user, not about should I give this program ability to get current time? This is not the question you want to ask. The question you want to ask is, should you allow this program to update your system? Or should you allow the program to get your current location? I think these are meaningful questions to ask the user. Right. So I think the answer to that question is the same problem exists in both capability-based system and in access control-based system. It's not like access control-based system doesn't have this problem. Access control-based system actually have the exactly same problem because it's higher than capability versus access control list. Also, like it or not, the world is moving toward that direction. Not in the fine-grained capability model I'm presenting, but in the coarse-grained capability model, all modern application models are moving that way. I don't think it's a very different category problem. Here's why. You can translate capability-based system into an access control list system by saying, I'm only making the decision of whether I grant the access at installation time and the process startup time instead of runtime. In that world, you can actually still have access control list on each of the resources you have on the system, and you can still have the code living in the capability world. You just make decision at a different point of time. Right. So I'll give you one concrete example, web server. I run web server in production. I know exactly what address I'm listening on. I know exactly which port I'm listening on. I'm listening on port 80, all right? So in the capability described in the manifest of the web server, I say web server listen on port 80, period. And then the system will provision the web server with a listener, TCP listener capability with port 80 access. It will not allow the web server to do anything else, like, for example, sending TCP, UDP traffic, or listening on port 81. It's just not allowed. Because of that, you actually, a lot of the Windows firewall functionality is already built in the system in a way. Make sense?
That is one example.
All right, so what? How does IPC work? Yeah, interprocess communication, that is the lowest level of the system. It's written in unsafe code. It has nothing to do with capability. It does use mutable shared memory in unsafe code. The API, I don't have an example for that. It's kind of like RPC where you declare the interface. So in Midori, the interface declaration is written in C#. You declare interface, C# interface, and you put eventual attribute on it. And then there's a code generation to generate both the stop side for the proxy and the server implementation side for your server base. And you implement the server, you use the stop for the communication. Yes.
So, just a comment, but especially with access control, so one of the things you guys are talking about is how you are shifting decisions to be made basically when the program is installed. Like that is one of the things that's exciting, right? And I would urge you to reconsider that because when we deal with breaches, it is very, very, very hard to evict an attacker if you cannot immediately terminate their access to something. So if your solution to, oh crap, this app has a little bit too much access and attackers are now using it to access these files, the solution to how you stop that is you need to simultaneously reinstall and reconfigure this program across our entire data center. I mean, we're never going to kick someone out if that's how we have to do things. Like, we need to be able to change these things.
Well, go back to the theme. If you figure out an app has a vulnerability and an attacker can use the app as a conduit to attack you, what you do is you terminate that process.
When you install bugs.
So that assumes that you know that the app has a bug, right?
Anyway, Scott reminded me the time. So we're already 5 minutes past. I'm willing to stay here, answer all the questions. I will stay as late as you want, and I'll hand over to Scott.
Okay, thanks, everybody.
All right. Thank you.